Welcome to ScienceCover.com. This session is on radiation. We'll begin by looking at the history of the atom and how we believe the atom is structured today. And then finally we'll move on to looking at how we believe radiation is caused by certain atoms. To begin, pause the video and complete the Do Now task. Check your answers to the Do Now task. Now let's move on to look at the history of the atom. The first idea of the atom was around 400 BC from a philosopher called Democritus. He suggested that everything was made out of small building blocks which couldn't be split into anything simpler. So he called these atoms, the word atom meaning indivisible. Over 2,000 years later, in 1803, John Dalton suggested that atoms had a spherical structure and that they could not be split up or divided into anything smaller. He believed that each different material was made out of a different type of atom. Almost a century later, in 1897, J. Thomson discovered the electron. Now, he found this to be about 2,000 times smaller than the lightest atom, and this meant that they needed to change the idea of what the atom may look like. So they took the spherical structure suggested by John Dalton, and they placed the electrons scattered throughout it. Now, since they knew electrons were negatively charged, this atom would push itself apart. So to prevent that, the inside of the atom was made positive charged. So what we've got is a positive charged sphere with negative charged electrons scattered throughout it. And this model of the atom became known as the plum pudding model. 12 years later, in 1909, Ernst Rutherford performed an experiment now known as the Rutherford scattering experiment. In this experiment, alpha particles were fired at a gold foil. Now, he used gold foil because he can cut the gold very thin and it keeps its structure. And the alpha particles themselves are a type of radiation, they're a very small positive charged particle. The whole experiment was performed in a vacuum as alpha particles can't travel very far in the air and he didn't want the air to interfere with the experiment. When he performed the experiment, he discovered that most of the alpha particles passed straight through the gold foil without doing anything. Some were deflected to the left or to the right, and some were actually backscattered. This means they were bounced back in the direction that they came from. So Rutherford's conclusions from this experiment were that some of the alpha particles were being deflected, and since he knew alpha particles had a positive charge, there must be something positive repelling them and pushing them away. Since some of the particles were backscattered, the positive charge must have a large mass, or the alpha particles would just simply push them aside. And since most of the alpha particles passed through without doing anything, this positive charge region must have been very small in size. So he knew that there was something with a large mass, small in size, that had a positive charge. Now, Rutherford had discovered the nucleus. So in 1909, the atom was redrawn to have a small positive charged nucleus at the center. The electrons were placed orbiting in a shell around this nucleus. In 1914, Niels Bohr carried out experiments to show that the electrons orbit at specific points called energy shells, and that they could move between these shells when they were given or losing energy. And so rather than having all of the electrons in one single shell, we knew now that the electrons were in separate shells. In 1932, James Chadwick discovered the neutron. So the nucleus was redesigned so that rather than being one small positive mass, it contained neutrons and protons separately. Now pause the video and complete task 1, numbering the events in the order in which they happened. Let's check our answers. The first event was that Democritus stated that everything was made out of simple building blocks. Then over 2,000 years later, Dalton suggests that atoms were like tiny spheres. The next event was that J.J. Thomson discovered the electron and created the plum pudding model. Then Ernst Rutherford's scattering experiment helped discover the nucleus. And then Bohr discovered that electron shells were separate orbitals. And the last event was that Chadwick discovered the neutron, and so the nucleus was redrawn to include protons and neutrons as separate particles. Question 2, we have to sketch the plum pudding model. So this has to be a sphere of positive charge with electrons scattered throughout. In the Rutherford scattering experiment, what type of particles was fired at the foil? Those are alpha particles. What was the foil made from and why? It's gold, as it can be cut very thin and it keeps its structure. Why was the experiment carried out in a vacuum? The alpha particles could strike the air molecules and they'd never reach the foil. What were the results? Most particles passed straight through. Some of the alpha particles were deflected, and about 1 in 1,000 is backscattered and goes back the way it came. What did Rutherford conclude? There was something with a positive charge that had a high mass but was small in size. Let's move on to look at what we believe the structure of the atom is today. This diagram shows the structure of an atom. At the center of the atom, we have the nucleus, which is made out of protons and neutrons. Orbiting the nucleus in shells, we have electrons. Now, when we talk about the mass of a particle, we talk about how many kilograms of material it's made up from. And we know that the proton and the neutron are roughly the same size mass. So we can compare their masses, and we call this relative mass. So if I call the proton's relative mass 1, then I have to call the neutron's relative mass 1. And the fact that these numbers are the same tells me that they're about the same size. Now the electron's relative mass is 1 over 1,836. And this tells me that the mass of the electron is much, much smaller than the mass of the proton and the neutron. The charge of the particles differs, so the proton has got a positive charge and the electron has got a negative charge. But since it's about the same size charge, then we can say that the proton is +1 and the electron is -1. And the neutron do not have a charge, so we can call their relative charge 0. Now pause the video to complete task 2, the structure of the atom. Let's check our answers to task 2. In the center of the atom, we have the nucleus, so this is the neutrons and the protons. In this particular diagram, it doesn't really matter which way round you put the proton or the neutron. But the electrons must be the smaller particles orbiting the nucleus. For the different particles, the proton has a relative mass of 1 and a relative charge of 1. The neutron has a relative mass of 1 and a relative charge of 0. And the electron had a relative mass of 1 over 1836 and a relative charge of -1. Now let's look at how the structure of the atom can cause radiation. The nucleus of the atom contains protons and neutrons. Now we know the protons have got a positive charge, and positive charges repel other positive charges. So the protons are actually pushing other protons away from them. So they're pushing the nucleus apart. Now luckily, there is another force acting inside the nucleus called the strong force. And this acts between all protons and neutrons, and it's an attractive force, so it's pulling the protons and the neutrons together. Now as long as these two forces are in balance, then the atom is stable. But if there are too many or too few neutrons in the nucleus, then the atom becomes unstable because these forces are no longer in balance. Now to try and regain its stability, the atom throws off some particles, usually at high speeds, and we call the emitted particles radiation. Now pause the video and attempt task 3. Let's check our answers to task 3. What causes the force that pushes the atoms apart? It's the electrostatic force of repulsion from the proton's positive charges. What causes the force that pulls the nucleus together? It's the force between the particles in the nucleus, and this is called the strong force. What happens if there are too few or too many neutrons? The force of repulsion and the force of attraction in the nucleus are not in balance. Particles get ejected from the atom, changing the nucleus, and these ejected particles are what we detect as radiation.